So topic fluids, and in this session we'll discuss the doubts related to this exercise assignment. The first question as a doubt is 16b2 and C. Okay, 16b2 and C. And this is question 16. In 1909, Robert Millikan did an experiment to find the charge on electron. A tiny charge oil drop was dropped between the two charge plates. The radius of the oil had to be determined so that the weight could be calculated. Before the plates were charged, Millikan observed how long it took for an oil drop to fall through air between the two fixed points. The terminal velocity, hence the radius, could be calculated. Complete a free body force diagram. So the weight will, if it is moving at a terminal speed, so the downward force must equal to upward force. Explain why the oil drop reaches a terminal velocity, so there is no resultant force, or we can say weight is equals to upthrust plus viscous drag. That's why it reaches a terminal velocity. Then this part B1 and 2, the values here, as you can see, for the first part, oil drop take 11 seconds to fall a distance. We have to, terminal velocity means constant, and when speed is constant, we can use the formula distance over time. The distance it fall is 10.2 millimeters, so it will be 10.2 into 10 to the power minus 3, and we convert into meter, and time is 11.9. So when we substitute, we'll get that as about 0.001 milliseconds. Then assume that the upthrust is negligible, so we neglected the upthrust, and show that the radius is about 3 micrometer. So how we can show that the radius is about 3 micrometer? If upthrust is neglected, it means the viscous drag or drag force is equals to weight. So as upthrust, because when it was moving downward, the weight, which is the downward force, is equals to upthrust plus the drag force. But upthrust is neglected here, so we can say that weight is equals to the viscous drag, and weight is equals to mg. So mg is equals to viscous drag or drag force, which is 6 pi eta r v. And we know the density of the oil, but we don't know its mass, so we can work out, because density is mass over volume. So density into volume will be equal to mass. So in place of mass, we can substitute density into volume. So density, volume, and gravity is equals to 6 pi eta r v. But volume directly cannot be measured, as radius is not known, and this is when Stokes law is applied. This formula is valid for spherical object. So volume of object is equals to 4 by 3 pi r cube, because we assume this as a perfect sphere. So the equation will turn or change. So it is equals to viscosity 4 by 3 pi r cube into gravity is equals to 6 pi eta r v. And we further simplify this equation before substituting the value. Pi will cancel with pi, and this is r cube, so 1 will cancel with r, and this will be 2, this will be 3, and we further simplify. So this will be 2, this density is there, 2 by 3 r square g is equals to, this is 3, pi is cancel, viscosity, and then v is the terminal speed. So v is the terminal speed, which we already calculated in the previous part, which was 0.001 milliseconds, meter per second. Yeah, meter per second was, so 0.001 meter per second is the velocity at which it is moving. So we have this parameter. Viscosity, the n, viscosity of the air, it is 1.82, but what is the exponent here? 1.82 into 10 to the power minus 5. Actually, this is minus 5. So here it will be minus 5. So we have the viscosity, we have the density of the oil as well, which is 920. So we'll have density. Then we'll substitute the values and get the value for R. So this is because the viscosity here was 1.82 into 10 to the power minus 5 Pascal second. So this will give us the value of, when we substitute the values, first we'll get R square, and then at the last take a root of the final answer to get the value of R. Then it is very difficult to measure the radius of such oil drop directly. Suggest why. So what is the reason why we are not able to measure the radius of this object? Because first thing, when objects are too small, it is difficult to measure, and it does not have a regular or a definite structure. It will change if we try to measure. So it's, when it is falling, its shape will change. So the two factors which make it difficult, number one, it is very small. That is one thing. And then number two, its shape changes. So it does not remain as a perfect sphere. That's why it will be difficult to measure this radius. Then part C, explain why it is necessary for Millikan to maintain air between the place at a constant temperature. Basically what happened, the temperature affects the viscosity, and viscosity affects the terminal velocity. So as there will be a change in temperature, the viscosity will change, and as the viscosity change, the drag force or the terminal velocity will also change. But we want to keep them same. That's why temperature affects the viscosity, you can say. And as the temperature affects the viscosity, and the viscosity, the change in viscosity affect the drag force or the terminal velocity. So these are the two factors which will affect, like, are interrelated. So the whole experiment result will be affected if the temperature changes. So this is one of the doubt. Question 16, B2 and C. Next is question 25A. A student investigated a motion of a small sphere falling through an oil. The sphere was released at the top of the cylinder containing oil, and the measurements were taken enable to measure the terminal velocity to be determined. Describe the apparatus student should use to measure and the measurements to be taken. Student does not have access to motion sensors or data logger. You may include a diagram. So student is investigating the motion of a small sphere as it is falling, and he want to measure measurement, so it enable him to measure the terminal velocity. So first we'll take a cylinder, a measuring cylinder, and that measuring cylinder is filled with a liquid. And then we drop an object, we drop a sphere, a metal sphere, but it should be small compared to the size of the container. It should be half or less than half the size of this sphere. And then how we can determine the terminal velocity? So we can place marking on the measuring cylinder equally spaced. Like the markers are there, which are placed equal distance. We can even have like a rubber band wrapped on this measuring cylinder. So how we can work out the terminal velocity? So we have the formula. So basically, like if I say this is marker A, marker B, marker C, and then there is marker D. So what we do, we measure using a meter rule or a meter scale. We can measure the distance between the marker, and we try to keep this distance same, like distance between the marker A and B same as B and C, and BC same as C and D. So we'll get the distance, and using a stopwatch we can determine the time. So how much time it will take to fall, like example, moving from marker A to marker B, marker B to marker C. And what is the reason why not only two markers, why we have interval? The reason is that because we want to make sure it reaches a terminal velocity. Once it reaches a terminal velocity, it will take the same time to cross each marker. So the distance is known, and the time between the marker is also measured by using a stopwatch. Once it reaches the top marker, we'll start the timer. When it reaches the bottom marker, we will stop the timer. Source of error is there, like reaction time is there, identification that whether it crossed the marker or it near the marker, that is always there. But measuring a distance between the marker using a meter rule and time using a stopwatch, distance divided by time, that will give us the speed. But one thing which you have to keep in mind whenever you're drawing, because to apply a Stokes law, the condition is that the size of the sphere should be very small compared to size of container. Because normally students, when they are drawing, um, involuntary, they draw a sphere of larger size. So that leads to deduction of the mark, like you will lose mark for the drawing, because that is not the right way, as the Stokes law is only applicable for an object which is small as compared to size of the container. Is it clear, discussion, that how we work out the terminal velocity? Next is 29B4. Okay. Describe how the results obtained and the graphical method can be used to determine the value of the viscosity of glycerol. So when you see the equation, this is the original equation. So how we can use the result and the graphical method to work out the viscosity? So if I simplify this equation, because this equation can be simplified, as we can see 4 pi r cube is common, 4 pi r cube by 3 is common both sides, and the gravity is also common. So if I take, like first I simplify the equation and then I will sketch or plot a graph for one of the parameter on y-axis, the other one on x-axis. So 4 by 3 pi r cube by 3 into g. If I take that as common, so it will become 4 pi r cube g by 3. So it means the difference in the density of the sphere minus density of the ball bearing minus density of the glycerol is equals to 6 pi r eta v. Then I simplify this equation. When I simplify this equation, pi will cancel with pi, and this will be 2, this will be 3, and this is r, which will cancel with the one of the r in cube, so it will left with r square. And if I move the viscosity other side, so what we are left with, this will be 2, this g will be there, the gravity, the difference in the density of the ball bearing and the density of a glycerol, then r square divided by this 3 is multiple, that here is multiplied, other side will be divided, so 3 multiplied by 3 will be 9, and viscosity also will move, so viscosity and then v. Now what we do, this equation which we have, so it means the terminal velocity is equals to 2g, the difference in the density of the two medium, r square by 9 eta. Now how we can use a graphical method to work out the values which we calculated in the graphical method. So graphical method is by plotting a graph. So means we'll draw a graph, but which quantity will draw y is equals to mx plus c. So on y-axis we'll plot v, the velocity is plotted on the y-axis, and on x-axis we'll plot r square. So on x-axis we'll plot r square. So our gradient, because all the values, and there is no y-intercept here, so it will be a straight line which is starting from origin with a positive gradient. So the gradient of this line is equals to what the things which are left other than r square, that will be the gradient. So gradient of this line is equals to 2g, the difference in the density of ball bearing and glycerol, divided by 9 eta. But we need the viscosity here. So how to work out the viscosity? Viscosity will be equal to 2g, the difference in the density of the ball bearing and glycerol, divided by 9 into g. Is it clear that how we can work out graphical method to work out the viscosity? Why velocity against r square we are plotting? Because these are the factors which can be changed. Like the parameters which you can change, I can change. If I want to repeat the experiment, the things which will change or which can be changed is the radius of the sphere. Like the density of the glycerol or density of a ball bearing cannot be changed. Gravity is constant. So the parameters which can be changed, so that's why we plot a graph between those parameters which can be changed. So r square is why r square, so that when we want to repeat the experiment, we allow the object to fall through the liquid, so we can change the size of the ball bearing. Like we can use very small, then a moderate size, a bit larger in size. So when we change the ball bearing, the radius changes, the size of a ball bearing change, the radius also change, and that will automatically change the terminal velocity at which they move through this glycerol. So for different, it will be a ball bearing made up of same material, like the density is not changing, but the size of the ball bearing or the radius is changing. So always plot a graph between the quantities which can be changed during the experiment. If the quantity cannot be changed during the experiment, then there is no use of plotting a graph, because it remains same. So we don't have to plot a graph for that. Then next is question number 31b2. 31 B2. So that was the question. Okay, the following photographs are taken at a 0.3 seconds interval. So these photographs are there, which are taken at a 0.3 second interval between them. So what we have to do, the first one is sketch the axis to label the lines to show how the displacement of a small bubble A compared with a large bubble B. So as you can see, these they are moving. So A is already, because we have to sketch a graph for the displacement from the me, like because we have to consider certain part as a origin. For example, if we consider this part as origin, so A is already above the origin. A is already have some displacement. So both ways are acceptable. Like if you consider separately, individually, I can consider origin for A. I can consider this is origin for A and the other one is origin for B, and then I compare. Or if I consider B as a origin, so already A is above the origin. A is already covered some of the distance. So when we sketch a graph, A is already, and you can see A is moving relatively slower as compared to B. How we conclude that? When you check the figure, the picture, B covered greater distance or the greater displacement compared to that of A. So it means A is moving slower than B, and displacement time graphs, the slope represent the speed. So for A, it is already have some displacement, it is moving slower, that's why means the slope is less steeper, but for B it is having a greater slope. And why B crosses A? Because when you compare the displacement of B with reference to the A, as in the even in the figure you can measure this. So the displacement of B from the starting position, like you take a center, and the last figure. So this is actual displacement of B. But actual displacement of A from the starting figure till the last figure, we take the centers. So you will find when you measure this, it will appear to be smaller than displacement of B. That's why when I finish the two graphs, the B is finishing above A because it covered greater displacement. And why steeper slope? Because B is traveling faster as it covered a greater distance in a same time interval. The photographs are scale of 1 to 12. By using the measurement from the photographs, what is the meaning of scale of 1 to 12? It means, like example, if in the figure you see 1 centimeter, in actual it is 12 centimeter. Or in the figure you see example 10 millimeters, so actually it is 120. So it is 1 to 12 scale. Calculate the speed of the bubble B from photograph 2 to photograph 3. So photograph 2 to photograph 3, and when you're measuring, you should take the same point. Like if I take the bottom of the first bubble in photograph, then for the third image, I should take the bottom. If I'm taking the first point for B, then I should take, so this will be the displacement. So what you have to do using a ruler or the scale, you will measure this distance covered. And like example, it can be, you use a centimeter scale, so it will be in centimeter. Say it is coming out as 0.6 centimeter. When you use a ruler or the scale, I don't have the scale to measure this, so 0.6 centimeter. But in actual, the scale is 1 to 12. What is the meaning 1 to 12? Like it is, the original figure is 12 times than this. So you'll multiply this by 12. So it will be 0.6 times 12. That will give us the distance travel. And what about the time interval? The time interval between the images, I think the between the images, yeah, the following photographs were taken 0.33 second interval. So time interval is already there. So to get the speed, as we know, speed is distance divided by time. So distance is equals to 0.6 multiplied by 12 divided by time interval. How much time it took? It took 0.33 seconds. So that will give us speed of this bubble from photograph 2 to photograph 3. Is it clear? This question. This was 31B2. Next is 39A2. 39A2. In October 2012, Felix jumped from a height about 40 kilometers above the Earth, and he used a balloon to ascend. It consists of helium envelope, as you can see in the figure. Complete a free body force diagram below for a balloon as it rose. So when it is rising up, the upthrust is there, and because it is rising, so means upthrust is more than the weight, and the viscous drag oppose the motion, so upthrust should be higher, and the drag force and the weight should be, the sum of drag force and weight will be smaller. Then write an expression for the forces acting, because it is rising up. So if it is going up, the, we can say upthrust, and there is a resultant force whenever there is a resultant, like if in the question, I'll read the full question, but if in the question they mention it is moving or rising at a constant speed, then we'll say the upthrust is equals to viscous drag or drag force plus the weight. But if it does not rise, like it is accelerating up, in that case, so I will read the full question, but here in this case, upthrust minus, or upthrust is equals to weight plus viscous drag. This will be the case when it is moving at a constant speed or rising at a constant speed, or but if it was accelerating up, then what should be my expression? Upthrust minus viscous drag minus weight is equals to ma, where m is the total mass. So in the question, as you can see, a balloon rose, the total weight. Yeah, so this is how the balloon is rising, and then you can see as the balloon, it reaches about the constant height. At this point, it is rising up, but it reaches about the constant height. In the question they did not specify, so if in the question they did not specify and we want to write equation, as they did not specify that it is accelerating, that's why we can consider, so we can consider that the forces are balanced. Like initially the upthrust is more than the weight and the drag force, but once upthrust balances with the weight and drag, it reaches a terminal speed or a constant speed. So these are the questions 16D. 16D. A student tried a Millikan method. Yeah, this is 16D. To find the radius of oil drop, the student dropped the ball bearing and record the time it took between the two light gates. Explain why this is not a good model. What is the reason why? Because student is dropping here a ball bearing in air. So when ball bearing is dropped in air, the ball bearing, the height is not sufficient, like the height from which we drop, that is not sufficient to make it move with the terminal speed. If that ball bearing was moving through a liquid, yeah, because liquid is having a greater drag force, so there is a chance that this ball bearing might reach a terminal speed. But in this case, because this is a steel or a metal and surrounding the fluid is a air, so less likely for a short distance. Like example, when we are dropping in a lab, maybe we can drop from 3 meter height or 5 meter height, but that is not sufficient height for a ball bearing to reach a terminal velocity. So why this is not a good experimental equivalence for assuming this Millikan oil drop experiment? Because when ball bearing is moving through the air, it won't reach terminal velocity because the viscous drag of air is viscous drag due to the air is very small as compared to the fluid. So the ball will continue to accelerate. The ball will not reach a terminal velocity because to apply this Millikan experiment, the ball bearing must reach terminal velocity. But here, the acceleration will not be zero. So as it is not zero, then the object will continue to accelerate. And this experiment is valid when the object is moving at a terminal speed or a constant speed and having a laminar flow of the fluid around it. But when we drop a sphere, the fluid flow won't be laminar, it will become turbulent. As the object is much larger, so the fluid flow also is, is affected by the size of an object as well. Is it clear, discussion? Anyone else having a doubt or a question related to this assignment, fluids? Any question or a doubt? 41B1, okay. 41. 41B1. A student wishes to estimate the power output of a heart. He argues that heart has to pump out blood at a speed v and raise to a height h above. He proposed the equation where q is the volume of the blood passing through a point per second and density of the blood. Derive this equation for p using a principle of conservation of. Okay, so how we can work out, basically the work done when we are pumping, like a heart is pumping the blood. So two things heart is doing, it is pushing the blood and it is, the blood is rising to certain height. So work done by the heart is equals to kinetic energy, or work done of the heart or by the heart converted into kinetic energy as well as potential energy. And the kinetic energy, so we can say the energy supplied here by the heart or the work done by the heart is equals to kinetic energy of the blood plus the potential energy of the blood. Then work done is force into distance. Work done is force into distance. Kinetic energy is half mv square. Potential energy is mg h. Now, if I divide this equation by time, the whole equation I divide by time. So this is divided by time, work done divided by time, kinetic energy divided by time, and power divided by time. So work done divided by time is power, because power is energy divided by time. So work done divided by time, or force into distance divided by time is power. Now half mv square, what is m here? As you can see, m can be modified. Density is mass over volume. So mass will be density times volume. And they mention here where q is a volume passing per second. So what is q? So example, when I write here, it is half. In place of mass, if I substitute density into volume, so it will turn out to be half. In place of mass, it is density into volume. And this is v square, that's the speed divided by time, plus density into volume, gravity, height divided by time. Now in the question they mention here that this q is what? It is volume per second. So basically q is equal to v divided by t. So v divided by t, this q is v divided by t, and this is also v divided by t. So when we substitute v divided by t as like q in place of v divided by t, so what is the final equation? It will be p, because of space I am using a left hand side. The power is equals to half rho, the density. In place of v divided by t, we can write q v square plus density v divided by q is capital Q gh. So the equation is derived. Is it clear, this part? Any doubt in this? The 41b1, that the work done by the heart is kinetic energy plus potential. But we want to derive for power, equation for power. So power is energy divided by time. So all the parameters we divided by time. And when we divide it by time, we just solve for, as in it's mentioned, Q is volume divided by time. So in place of volume by time, we substituted capital Q. Any other question or a doubt related to this assignment, fluids?